If you're building a modern retrieval augmented generation pipeline, conventional wisdom dictates you start by spinning up a vector database. But there is a glaring anomaly in that conventional wisdom. Even highly optimized enterprise RAG systems consistently hit a hard ceiling, stalling at roughly 60 to 75% accuracy when queried on complex professional documents. This shows the root cause: vibe retrieval. Embedding models fetch text based on semantic similarity, lighting up nodes based on keyword overlap, but ask for a year-over-year margin, and it pulls a summary mentioning margin, missing the actual data table entirely. Mathematical similarity is a flawed proxy for actual relevance. Standard vector pipelines map spatial proximity, making them structurally misaligned with the demands of complex enterprise data. This brings us to PageIndex. Developed by Vectify AI, this framework operates on a contrarian thesis. It completely eliminates vector databases and semantic chunking from the RAG pipeline. Instead of taking a massive document and breaking it down into arbitrary, disconnected text chunks, PageIndex parses the file to extract its natural, hierarchical structure. It discards cosine similarity entirely. In its place, the framework uses explicit top-down LLM reasoning to navigate the extracted information. The architecture shifts from a rigid, fragmented database into an interconnected, organic decision structure. True relevance requires active machine reasoning over a structured hierarchy. To understand how PageIndex routes a query, we have to look at its explicit inspiration: AlphaGo's ability to navigate complex, multi-layered game states using Monte Carlo tree search. This diagram illustrates the first phase. Just as AlphaGo max tensile moves, PageIndex parses a massive document into a matching hierarchical table of contents. Each node within this tree is explicitly defined, containing section titles, summaries, and precise page ranges instead of uncontextualized text. At query time, the large language model takes over as an autonomous routing agent, evaluating the entire tree top-down. It actively reasons at each junction to determine which branch holds the answer, discarding irrelevant sections as it drills down to the target node. By eliminating brute force embeddings, this method perfectly simulates how human experts naturally navigate and extract knowledge from complex manuals. To test this approach, we look at FinanceBench, the industry benchmark for evaluating complex financial document QA capabilities. Traditional enterprise vector RAG systems consistently hit their 60 to 75. While the standard vector cluster sits stagnant, Maven 2.5, powered by PageIndex, rockets to a verified 98.7% accuracy. This massive 30-point gap is directly attributable to the two-step tree generation and LLM reasoning pipeline inside the framework. A secondary benefit emerges from this architecture: full explainability. Every single retrieved answer points back to an exact page and section reference. Achieving near-perfect retrieval accuracy requires abandoning black box vector math in favor of traceable, verifiable logic paths. Plain text is one thing, but professional documents rely heavily on complex layouts, embedded charts, and dense financial tables. Standard optical character recognition routinely strips away the structural context, ruining the data before the LLM even has a chance to read it. PageIndex bypasses this bottleneck with a vision-based RAG capability. The framework allows the LLM to skip OCR entirely and reason directly over raw page images, preserving spatial formatting. But parsing a single complex PDF leads to a much larger operational problem. How does a tree search system route queries across millions of distinct documents without failing? This diagram illustrates the solution: the PageIndex File System. Individual document structures link upwards, converging into a massive, overarching master corpus tree layer that scales reasoning across the entire database. Tree reasoning serves as a complete routing infrastructure, capable of navigating massive enterprise data lakes. That 98.7% accuracy metric is compelling, but it comes with severe operational penalties. The compute cost is massive. Because the system must actively evaluate branches at every junction, a single user query requires multiple sequential LLM API calls. This introduces a heavy latency penalty. Tree traversal takes several seconds per query, completely destroying the millisecond response times expected from vector indexes. You trade cost and speed for precision. High accuracy sits on one side, counterbalanced by multiple LLM calls, latency, and restricted processing. Deployment reflects this. The open-source version relies on basic parsing, locking enhanced OCR behind paid cloud services. Furthermore, the GitHub repository shows over 60 unmerged pull requests, indicating a small maintenance team struggling to keep up with community contributions. Architectural precision is no longer a mathematical mystery. It is simply a matter of how much compute budget and latency a team will burn. Given these parameters, the ideal use cases are strictly defined. This architecture dominates in financial analysis, detailed legal review, and strict regulatory compliance. Conversely, you should avoid it entirely if your environment requires real-time web search, processes unstructured chat logs, or powers generic consumer chatbots. Unstructured, contextless data simply does not benefit from tree reasoning. Standard vector indexes treat documents as static coordinates in a spatial map. PageIndex treats them as a logic problem, solved through active tree traversal. As the raw cost of LLM inference continues to drop, the critical question becomes, will the sheer speed advantage of vector databases eventually fail to justify their lack of precision? If this architectural breakdown saved you time, subscribe to the channel to stay ahead on future tool reviews. And if you found this next-generation RAG analysis useful, stick around for our upcoming deep dive into another framework that is rethinking how we interact with documents. As models gain the capacity to navigate document structure through logic, mathematical similarity is becoming an increasingly unnecessary compromise.